The IEEE is the Institute of Electrical and Electronics Engineers. It's the largest professional society in the world, and given the role technology plays in our life, has a huge influence on everything we do. The IEEE maintains over 4,000 standards, and not surprisingly, a standard for floating point arithmetic is one of them. Let's discuss that, as it's used in all the computers that you're working with. There's a standard for both single precision and double precision. Single precision uses 32 bits, 1 bit for the sign bit, 8 bits for the exponent, and 23 bits for the fraction, for a total of 32 bits, and they're arranged in this way. The first bit is the sign bit, followed by 8 bits in the exponent, and finally the 23-bit fraction. Double precision is a 64-bit number, 1 bit for the sign bit, 11 bits for the exponent, giving a wider range, and 52 bits for the fraction, giving more precision. This is arranged in the same order: sign, exponent, fraction. The only thing that remains is how to interpret the bits and come up with a number. So those additional rules are what we'll cover in the next few slides. We'll only focus on double, though exactly analogous rules can be used to determine the value represented by these representations in the case of single. We'll start discussing normalized numbers. First, let's draw all the positive numbers in this number system, double. Remember, it starts with the fundamental interval 1 to 2, and then many doublings of that, many halvings of that. The representation involves 64 bits, an 8-byte number, starting with a single sign bit, 11 exponent bits, and a 52-bit fraction. Right now, let's focus on the exponent bits. E is an 11-bit binary number. The value of E, expressed in base 10, ranges from 0 to 2047. Of those 2048 different values, values from 1 to 2046 are associated with the normalized numbers. The 52-bit fraction, f, selects one of the 2 to the 52 numbers in the interval 1 to 2. That basic interval has 2 to the 52 numbers evenly spaced from 1 to just less than 2. The notation 1.f sub 2 identifies that number. And finally, scale that number by 2 to the e minus 1023, add on the sign bit, negative 1 to the s, and that's the value represented by this 64-bit pattern. In these formulas, e is the base 10 version of the 11-bit exponent, so it's a number between 1 and 2046. This formula precisely gives those groups of intervals as the normalized numbers. The choice of f selects one of the numbers in the interval 1 to 2, and then the choice of e selects which of those intervals to use. E equal 1 represents 1022 halvings, and e equals 2046 represents 1023 doublings. The whole range is achieved. There are 2046 intervals represented, and each interval has 2 to the 52 numbers. So there are 2 to the 52 times 2046 positive normalized numbers. That many negative normalized numbers as well. Next, let's look at the unnormalized numbers. First, draw all the positive numbers in the number system, and then again, focus attention on e. On the previous slide, we saw that the values 1 to 2046 represented normalized numbers. E equals 0, in other words, all 11 bits equal to 0, is associated with the unnormalized numbers. The 52-bit fraction f selects one of 2 to the 52 numbers in the interval 0 to 1. Those have a spacing of 2 to the negative 52, just like the interval from 1 to 2. It's just shifted 0 to 1. 0.f, base 2, is a notation for one of those numbers. Then scale that number by 2 to the negative 1022. That scaling squeezes the blue interval from 0 to 1 all the way to the green interval. Add the effect of the sign bit, and this gives the value of the representation of this number. So this is relevant when e is all zeros. Precisely gives all the numbers in the green box the unnormalized numbers, 2 to the 52 of them, simply by selection of the fraction bit. The exponent is already built in, at 2 to the negative 1022. So the unnormalized numbers fall in the green interval, and the normalized numbers fall in all intervals to the right of that. Lastly, let's consider inf and not a number. Remember the layout of the bits in the 64-bit double. Inf, negative inf, and not a number are represented when e is equal to 2047. On the previous two slides, we've covered the case 1 to 2046 for normalized numbers and 0 for unnormalized numbers. On this slide, the last value, 2047, is important. So if e is 2047, which means all 11 bits are equal to 1, and f equals 0, then the value is interpreted to be inf or negative inf based on the sign bit. These are unique. There's only one representation for infinity and only one representation for negative infinity, and it's exactly this. E equals 2047 and the entire fraction bit equal to 0. If the fraction bit is not equal to 0, then the value must be interpreted as not a number. There's so many choices for the fraction being not 0, there's actually 2 to the 52 minus 1 different ways to represent not a number. As I understand it, an original idea to use all these different representations of not a number was to encode information in these when a calculation generated a not a number. I'm not sure to what extent that was done, and there's no documentation in MATLAB that describes how one can interpret different representations of not a number. Finally, just to reiterate what we saw on the previous two slides, if e is not 2047, then the 64-bit pattern does represent a finite number. So we've covered all the possible values of e. The sign bit is easy, and every time we were working with e, we covered all possibilities for the fraction bit. So with that discussion, as long and drawn out as it was, we've actually covered a lot of combinations for a 64-bit number to be interpreted as a double. In fact, we've covered all the combinations. If you go back and look, every possible pattern has been accounted for and has an interpretation.